Welcome everyone. My name is Maciej Grochowski. I was working for last couple of months on fuzzing NetBSD kernel. However, this knowledge also applies to fuzzing other kernels. It shouldn't be hard to get this working also on FreeBSD. I was also doing some work to get this on FreeBSD, so you can also apply this to fuzz your FreeBSD kernel. So the outline of the presentation, first of all, what we are trying to achieve, and this talk also assume that you don't have a lot of knowledge about the fuzzing and breaking the kernel. So this will give you a pretty good overview what you can do, what techniques are available, and some background knowledge like how these things works under the hood. So we'll talk about the coverage as a kind of feedback for our fuzzer that is used for the fuzzing. I will also mention a little bit sanitizers, but I won't go too deeply to sanitizers because this is also a very wide topic. However, yesterday was a very good talk about sanitizers on VM dev room, so if you missed it and you want to learn more, you can also see the recording. We'll also show how to do the basic setup for the fuzzer, and as a demo we will try to run fuzzing on the FFS on NetBSD kernel as a virtual machine. So hopefully we may find something interesting. Sure. Okay, so first thing to justify why are we trying to break things, or why I'm doing this, is essentially need for having multiple different ways to improve the quality of software. And as we all know, kernel is a very critical part of the operating system. If you break the kernel, you have serious issue. And there is no known silver bullet to solve all the issue and ensure software quality. So usually what people does is multiple parallel actions to improve code quality and software quality in general, because we know we always will have some bugs or some issues, but from the other side, we would like to have reasonable quality software and something that won't break very easily. So we can have some list with things that we can do to improve our software, starting from stuff like getting code reviews, applying best practices, and so on and so forth. This list is far from being complete, and probably it can be a couple of other slides to just list different techniques that we know. But I think one of the most important and most interesting, or some other people may say boring things, is about testing the software. So for me, testing is like the time when software meet the truth. So if you just do the reviews, if you are just doing analysis of your code without testing, without running the software, of course, it's not good. From the other side, technique is also very wide area. There's a lot of resources how people do testing. But I think in our context, it's fair to say that fuzzing is also a kind of testing for our software. So first of all, what the fuzzing is. Usually we call fuzzing when we have some way to test the software which expects some input, and as a testing technique, we are trying to give our program some strange, unexpected input, and we are observing what is the behavior for this particular input. So the simplest fuzzer that can be written is just, for example, let's say we have some binary that we would like to fuzz, which is called fuzz binary, and this binary gets us an input 1000 kilobytes and some raw byte input. So what we can do, we can just write some very dummy fuzzer in a couple of bash lines, or even in one if you like, very long sentences, and just get some random input, save it somewhere, or pipe it to the binary and then run binary. And the funny thing is, if this if the program is not written having validation in mind, in that way you already can break some programs, which is very funny. But the good thing would be to think how we can improve our dummy fuzzer. So what we can do to get the fuzzing smarter. And one thing that came usually to head is how we can generate the input in more intelligent way, more smarter way. So one of the technique is mutation-based fuzzing. So mutation-based essentially assume that we can come up with some strategies that will be smarter or have some logical sequence instead of just getting the random bits. And we can, based on those strategies, we can mutate the input and provide this input to the application. By definition, mutation-based fuzzing doesn't really care about the state of application because we are just caring about strategy. So we have some strategy to flip certain bits, or the strategy can also be aware about the grammatic. So for example, if you are fuzzing the HTTP requests, you can get some payload, which is like in order with HTML standard, and then play with different tags. You don't have to have just raw bytes that you are modifying. So in that way, we are able to much easier find some interesting inputs than in just a random way. And also, if you get a random input, usually if your program expects some different tags, some different header in the input format, you usually just stopping on some first couple of checks that are making sure that your input is have some, for example, certain header, certain pattern at the very beginning. Another way to improve the fuzzer is introducing the feedback loop. So in the feedback loop, essentially get some feedback from running application about application state. And this state can be measured in different ways. The most popular one is the coverage, code coverage. But we also can think about other things like timing, CPU resources, and stuff like how application behave with the environment. And so funny thing, when I was doing those slides, I just put timing because, first of all, timing is known from cryptographic software. So for example, if you have some cryptographic software which have different timing for different requests based on the execution path, you obviously have security issue. But I was thinking, yes, that's a good example, but from the other side, I didn't saw many like timing-based fuzzers. And yesterday when I was waiting for my FOSDEM t-shirt, I met my colleague, he's working for Tor project, and we started talking. And I told him, oh yeah, I'm doing the talk on BSD dev room about the fuzzing. And he was like, oh really? I have a friend who actually was doing a fuzzing based on mutation. And he used a timing for execution of this program to the firmware. And based on this execution time, he was doing modification to the software. And by this way, he was able to break some popular electronic device. So I was like, oh, really? So that means this really works. So yeah, I will also try to deep deeper in this timing way to measure the feedback from the application. So it was pretty funny. Also from the testing world, we have stuff like we can think about our fuzzing based on the application that we fuzz. So if, for example, in similar way as we are doing testing, so we have white box testing, black box testing. If we don't have, for example, all information, but we have some information, we can also say we have gray box testing. So this feedback loop also depends what kind of fuzzing are you doing. In our example, we'll be doing white box testing because obviously we have a kernel that we can compile, we can instrument the code, and then we can monitor the state of the application based on those informations. So coverage tracking. As I said, that's one of the main technique how we can get the feedback from the application, and that is how many fuzzers works. Main coverage trace is PC trace, program counter. It tells us about the execution path. And the good thing, how we can start our understanding of this format is essentially the way how it's stored in our program. So whenever we run the program, or whenever we have a kernel, because kernel is also a kind of program, we need some array, we need some memory location where we will be putting the sequence of PC counters. So in our example, we have an array of size 100 with 100 entries, but it can be much wider. And when the program is executing, this can be done, for example, per thread, per process, or if you are running the kernel, it can be also something per kernel thread, but also you can think about some global array. For example, if you don't care about the threads, but you care about the execution path, because what can happen if you are fuzzing the networking, you can put the request to the networking queue, and then another thread will be getting this request from the queue. So if you are fuzzing based on the thread, then you will be just seeing the path when you put the packet to the queue, instead of seeing another thread, which can be different, that will be processing your request. So how this exactly works, as I said, those are compile time instrumentations, so they are put by compiler. So on the right, we have a program, very simple, which have main, which call bar, which call foo, which call bar. So what will happen during the compilation phase, our compiler will put some magic instrumentation at the very beginning of all functions, and those will execute when we are executing the program and won't interact with our program. But what are those magic instrumentation? So I get a code listing from NetBSD kernel, and it's a little bit modified just to give you some brief idea what is going on. So every time when we hit the instrumentation, we call this function instrument code, and this function need to get our memory that we reserve for presenting the PC counters. And we obviously get the index because we need to write another entry. We also need to do stuff like border checking, because based on also your intention, you sometimes may overflow, and if you do, the question is for you what you would like to do. But the most important part, we are just getting the PC from the function from which we were called by just compiler macro. So if you run our very simple program, we'll end up with array of 3 entries, main, foo, bar. So it's very straightforward. And we don't have only PC trays. We have also a couple other different trays. We have CMP, diff, and GP. What they are? CMP trays is used for application, or is used to instrument the comparison instructions. Diff is for every time when you're doing division between the arguments. GEP is for manipulating indexes of the arrays. So compiler have some understanding about those, and when it compiles the code, it will put the instrumentation before every instruction is performed. So then you can have better understanding why you need to have different types. And so you can imagine, like, based on your program, you may doing some mathematical operations, like you can compare the argument. You have some graph or some tree that you are traversing. So only the PC counter doesn't give you full information, because you may always see the same path. However, the path is not the same because you are just getting different arguments. Or if you are manipulating a lot of indexes of array, you may also see the same function called over and over again, but from the other side, you use different arguments. So I here present the CMP trace. It's a little bit different than PC trace, but from the other side, it's something that also you have in all BSD kernels, as far as I know, and also other ones are similar in terms of format. So instead of just one information, you have arguments of the operations. So we have the numbers that we are comparing. The types tells you about the size of the argument. So if it's 8-bit, 16, 32, 64, so on. And also you have PC trace. So you have a sequence of those sets of 4 values inside your array. And as I said, everything depends on your kernel, on your code that you're fuzzing. So depends which part, for example, of the kernel are you trying to fuzz. It's always good to think, okay, so if the PC trace is the only one that I would like to see in my fuzzer. Other important tools, sanitizers, as I said, I won't be going how they actually works, but I'm trying to convince you that they are very useful. And the reason why they are very useful is when you meet any issue in your code, the code may not exit after invalid operations performed. For example, you can have memory corruption, but this memory corruption won't expose easily. So in that case, you can run the fuzzer and then don't have any crash, even if you corrupted some data. So if you get the sanitizers, here we have 3 kernel sanitizers, address sanitizers, leak sanitizer, and memory sanitizer. They are available in NetBSD. You can also have undefined behavior sanitizer. There's thread sanitizer. I didn't know too much about thread sanitizers at this moment, but I am also looking about them. So the very simple one to start with is Kasan, because it detects things like out of bound for chip stack and other like common mistakes from the software. The downside is you cannot have all at once because some of them are mutually exclusive with other ones. So for example, you cannot, by definition, you cannot have ASAN and MSAN, other sanitizer and memory sanitizer, because they are relying on the same data, so they are overlapping each other. So in LLVM, it's specified that you cannot use both. From the other side, they also provide some slowdown because they are compile times, and they also introduce another instructions. But as I say, they allows you to fuzz bugs easier and faster. So I think is very is big leverage for the fuzzer to actually run your fuzzer with address sanitizer or any other sanitizer. Depends on also what kind of bugs are you expecting. Let's go to the fuzzer. The one that I was using for a couple of months is American Fuzzy Loop. I think everyone knows American Fuzzy Loop is very popular. It has very good record for found bugs. Some people also claim it's pretty old at this moment, but I think like as a starting point it's very good because first of all it's very easy to use. It's rock solid. But from the other side, it didn't have a goal to fuzz the kernels, but just the user space, but just the user space program. So you cannot use it directly to fuzz your kernel. You need some modification. So what that modifications are? We can think first of all what we have from the kernel side, what we have from AFL side, what format AFL require. So Unix's Linux, FreeBSD, NetBSD, OpenBSD, and other expose the coverage using coverage device /dev/kcof. Using this device, you can get, for example, PC trace, CMP trace. The way how you access this data, you configure the device using ioctos, and then you do the memory map. Then you run your program. And after you finish, your mapped memory should contain those arrays that I discussed previously. From the other side, AFL uses its own specific format where AFL focus on pairs of the PC counters. So it stores unique PC counter pairs, which mean every time when we perform another instrumentation, which means we have another PC, we remember the old PC counter or 0 if we just started, and then get the old PC counter and current PC counter, XOR them together very easily, make sure that we don't overflow, and then increase 1 in our map, which gives a compiler, which gives a fuzzer hint. This pair of those 2 PC counter just happened. So then the fuzzer can analyze this array and say, okay, so I got another pair that I didn't saw before, or maybe I always get the same pairs of PC counters, which mean I need to do something different. So it's very easy to convert PC trace to AFL trace because they look the same. But from the other side, we don't even have to do that. We can just store, because it's just storing redundant data, we can just do this on fly. So we can store two values and this map. And this is everything that our AFL needs to work. In order to do that, we did some work and modify a little bit NetBSD kickoff. And essentially, we allow you to plug in another kernel module, which will hook to the coverage functions that are already there. By doing that, you don't have to manage the default resources, but you still can use them if you like. But from the other side, you can do things like, as I show, like converting one input from coverage to another one. You can think about any other type of fuzzer that you can use, and you don't have to copy all kickoff code and then manage file descriptors, make sure that threads are open, closed, all of those things that you need to copy from kickoff. You can just focus on coverage functions and mmap. That's what you really need, and then you can leverage on what is written already. Okay, so how this looks. First of all, when I think about the fuzzing, I first of all think what is the input, what is the output. So here we have my setup for fuzzing the FFS mount. So my input is my file image. My output will be the result of mount or kernel clash, and this sequence also require a couple other things like a wrapper. As I said earlier, there's like a plugin for kickoff, and it works like we have a fuzzer. The fuzzer create the file system image. We need a wrapper that will prepare the file system image to be mounted, but also will execute the code that we need. So it will be executing the mount. Also, we do not trace the wrapper. This is just a thing that helps us to trigger the execution path in the kernel. Then we do the mount. Mount is calling syscall, VFS, file system layer. On all of those layers, we get the coverage data. This coverage data then is transformed by our AFL plugin. This plugin is exposed to the fuzzer as this map of the pairs that I showed before. And then after every run, the fuzzer will get the input, run the input, we'll get the output from the shared memory. We'll see, okay, so what different strategy as our feedback we should change, or did we found any interesting things? And after the feedback phase, it's just perform another operation over and over again until we hit something interesting. So I would like also to talk a little bit more about the wrapper itself, because also it's interesting. So the way how you usually write those wrappers is I write them in shell. I focus, okay, so what kind of operation I'm doing, and then after I'm done with shelling, I need to translate to some other better performing language. I usually just use C, but you can use C++ or anything else that can expose your raw interfaces like system calls, because you don't want to run on top of someone else's libraries. You just want to have the simplest, maybe not even the simplest, but the shortest code that you can do. And this is also well documented on every fuzzer that the performance is very key. Even if your fuzzer is very smart and doing very good guesses about different inputs and then analyzing the output very well, it still can perform much worse than much simpler fuzzer, which is just faster, because in order to find some bugs, you'll need to run this 10,000 times, million times iteration, maybe even billion times iteration if you have some very well-tested software. So in that regard, you need something that is performing operation very quickly. So remember, performance is the key. Use raw interfaces. Other things also that are useful when we are doing the fuzzing is how I can see what is going on inside my fuzzer. And for example, what the problem that I had was when I ran my first fuzzer, and it was the first fuzzer I saw like it's not very slow, but from the other side it's very ineffective. So I was thinking, okay, so what's going on inside this fuzzer? How I can debug that? So then what I did, I ran the kcoff on my fuzzing wrapper, and I monitor what kind of execution path is inside so by the fuzzer. And I realized, for example, in NetBSD, we have much more verbose kernel, and we get a lot of operations from virtual memory. Even if you are doing mount, you see more virtual memory operations, which mean you're actually not fuzzing the mount, you're fuzzing stuff related to the management of the pages. So this is also a bit tricky, and for example, in this way you can get the input, you can understand what is actually going on under the hood. Other thing that you can also do before you start, or if you would like to tune something, is also doing coverage benchmark, fuzzer benchmark. So you can see, for example, if you want to understand if your wrapper is fast or slow, you can, for example, put some very dummy code inside the kernel. What I've done was create some simple some simple character device. We just get some input, compare this with the pattern, and then if the pattern match, you won the lottery, so your kernel crash. If it doesn't, you just run over and over again. But then I can see how well my, because this code is very simple, I can see how well my operation in my wrapper perform. And from the other side also, you can compare this, this kind of check with user space, which also gives you some intuition how well are you doing. So to do the local setup of the fuzzer, we also need to have some initial corpus. So this initial corpus, you can create the corpus from, for example, just raw zeros. It's very well documented that the AFL is able to reproduce some different formats. So for example, if you are fuzzing the JPEG or some other images, AFL is able to reproduce those images. But from the other side, if you are running a little bit slower because you are in the kernel space, and also you don't want to spend like a initial CPU cycles just to figure out what is the header or what is the magic number for the file system inside the image, you can just create one and provide this as a raw initial data for the fuzzer. So this also very helps with speeding up the fuzzing. And once we have that, we can run our fuzzer with option K, which was added in AFL by guys from Oracle when they also were doing the fuzzing of file systems. So essentially, I reuse their work and integrated this with NetBSD and FreeBSD to make them work for both. And then you also need to specify the wrapper. So the important thing is, in that case, you're fuzzing the same binary that you are running on. So do not shoot into yourself in foot, because if your kernel crash, then your data may disappear. You may even not see the latest output in the AFL. So you need to make sure that you know what you are doing. So if, for example, you are fuzzing something what is unstable and you will be finding a lot of bugs, maybe it's good to get this input and output somewhere outside of your kernel, so you can mount this on NFS, for example. It will be slower, but from the other side, you will have less issues, and then run this process remotely. Because if you don't, then every time when you crash, you can lose the data that you are looking for. But from the other side, if you have well-tested software and you just will be happy if you will find a couple of bugs or maybe one bug even, you can just run this natively on your kernel What I've done, for example, was connecting the debugger to the kernel, run AFL. If anything crash, I can just get output from debugger and see what's going on. I can also get crash somewhere. Sometimes I realize that depends on the path that should crash. You still may not get the, you still may have some problems with getting the output. So because the ideal scenario is you get the output, which is the latest image that you were fuzzing, and then you can get this image and check, okay, so if this image always break my kernel, or if this was something that was from some before testing. So usually it's very nice if you have output that is a payload that you can just mount and then and break your kernel. Okay, so how many iterations to find a bug in fuzzing FFS? So what we'll be doing, we'll just run on the same virtual machine, the fuzzer, and that's actually some other issue that I found at the very beginning, but hopefully we can find something interesting. Okay. Okay, so I need to get, I don't know how big it can be, because then the fuzzer needs to also, okay, so we have here the fuzzer, it's modified version. We have inside in a file, which is our prepare, it's not 0, so the name is a little bit misleading, but we can see that, oh, this is 0. Okay, I was fuzzing this, anyway. It's actually this is 0, so I was fuzzing this before, and I think, yes, well, thanks. Okay, so it's not 0. So you can see this is the legit file system image. So we have the offset, which is 8, I think 8K, and we have some magic from the headers of FFS. I won't go too much in details, but we see the structure is it's not just a 0 file. So the way how we run it, we can have this. Okay, so I won't run it yet because I usually also get wrapper as an absolute path. Wrapper mount. So we run AFL fuzz -k, I from input, out from output. I didn't remember exactly, but I think this definitely will work if we will get the wrapper itself. Okay, from the other side, this running on GDB. So we have connected debugger because this is just a virtual machine, and this is debugger that is debugging the kernel. So we can stop in every time. We can see the trace. We can continue trace. We can also see that because we stopped, virtual machine just froze. We can just continue. So then our virtual machine is still living. Okay, let's run this thing. Oh, we already get something. So this run the dry. So this run the. So it was running the dry input, the dry run at the very beginning. So at dry run, it's just do some simple modification, and what we can see here is, yeah, usually it also should show you the AFL console, but because we hit something, probably because I was testing this before, so we have some old history. So it was also running something that was found before, but we can go here, and this is already running in getting the core dump from the kernel. Okay, but we have operations that crash. So we have VFS reclaim. which was called on the vnode that was reclaimed from the vcache. So that's kind of moment when you start debugging the kernel, and I won't right now be doing this because it requires some time, and also I'm not in the right now great position as a presenter to start debugging that. But this is something that broke our kernel. So this might be related to the data from the vnodes, and this we can get this as a core, or we can start debugging this. We can start debugging this in GDB. Okay. I think we can just go this one. Okay, so conclusion. So fuzzing the kernel is another way, as I said earlier, we need a lot of different ways to test our kernel that we can just do to make sure that our quality of our drivers, our file systems is better. Also, if you like to start searching for some bugs, this is also very easy way to start. And we have recently a lot of good work for improving things that allows us to run the fuzzing. So for example, gathering the coverage in NetBSD and other BSD in general improved. Also sanitizers, in particular in NetBSD, become much better over the time. It's very easy to start, as you see. It doesn't require much knowledge. So I think in this half hour I gives you almost everything that you need to start your adventure with the fuzzing. And also you should run the sanitizers. By the way, this was not run on sanitizer because we didn't have any sanitizer output. So future work, I would like to have some also discussion with other people. I saw Andrew presentation from FreeBSD that he's also doing something on AFL. So maybe we can came with some similar way that we fuzz BSDs. I saw previously on Linux they introduced another device. It was /div/AFL, which community didn't like it, and it was not upstream at the end. So I think if we will try to get this on common interface, that will be beneficial for everyone, because then people from security projects can just fuzz our kernel in the same way. I also need to spend more time on improving the remote fuzzing, because it didn't scale very well if you want to find many bugs, and just continue with fuzzing and fixing the bugs. The resources, so our NetBSD blog, there's also paper, Oracle paper, yes, from 2016. My collection of mount wrapper, Clang documentation also is very useful source of information, and I will be happy to get any questions, if any.
Any questions? Okay. So thank you very much.
Thank you.
One group, just because we can listen to the questions and the answers.
I would like to thank you for the talk. I would like to ask you about, is it possible to use APL, amerikanische function, for remote fuzzing?
Please repeat the question.
Okay, so the question was, can you use AFL for remote fuzzing, not for the fuzzing that was presented? The answer is yes, but you need to do additional setup, because, as I said, AFL use the same data on use input and output directories, so you need to have them remotely. You need to run this as a process, and then you need also some way to send back the information to the fork server that crash happened because your process just stopped. And the thing that I'm currently looking on is how to get efficiently the kernel dump, because then you have the dumping process. So this allocation for dump also need to be mounted for something like NFS again, or some other protocol. I mean, NFS is the simplest one, but you can potentially come with some other good ideas. And I don't know how hard will be to get AFL console to analyze those crashes, to say, because when you're fuzzing the user space library or user space binary, you see those unique crashes, for example. So AFL is going through the core dump of the process and then saying, okay, so this one occurred before, so then it's not unique, it's like something similar, or this one is not unique because it's something different. And then AFL also takes strategies from those crashes to improve. So I think, as I said, that part about analyzing the core dump from kernel is some unknown for me. Other things can be done easily. Go ahead.
Another question.
Okay, maybe someone wants to leave the room before the second question. Okay.